Alright guys, welcome to lesson 10 for unit 3. We're going to talk about doing limits with trigonometric functions, and we're going to primarily be focusing on how to do that with L'Hopital's rule today. So let's go ahead and review some basic trig facts here really quick. Sine of 0 is 0, cosine of 0 is 1, and tangent of 0 is also 0. We're going to see a lot of those today, so it's nice to have those locked in your mind up front. So let's go ahead and begin with our first example here. Let me pull up some problems to work on. All right, so we're going to do a couple problems here for example 1. So we're going to try some direct substitution here first. I'm not going to put those equal signs yet because you may end up with weird things which you can't have equal signs with, right? We talked about that last time. All right, so tangent of 0 is 0, and 4 times 0 is 0. So sure enough, we end up with that indeterminate form, which tells us, uh-oh, it's time for L'Hopital. So therefore, by L'Hopital, we can say that the limit as x approaches 0 of tangent x over 4x is equal to limit as x approaches 0 of the derivative of each of those things. So the derivative of 4x on the bottom there is pretty straightforward. That's just going to be 4. The derivative of tangent is secant squared x. All right, so we're going to go ahead and do our direct substitution here, and we're going to get secant, and I put an equal sign this time because we're not going to get a 0 on the bottom. We've only got a 4 down there, so it's impossible to get a 0. Let's go ahead and figure out what secant squared 0 is. Now, in case you guys forgot, secant of 0 is the same thing as 1 over cosine of 0, and cosine of 0 is 1. So we end up with 1 over 1. And if we're going to square this, we still end up with 1, so it doesn't matter. So the top is just going to be 1, and we end up with 1/4. Okay? All right, let's go ahead and check out another one here. A couple of these show you a variety of different situations. All right, so let's go ahead and apply the limit here. If I apply the limit to 1, that's just a constant, so the 1 stays the same. And if I apply the limit here, that's going to give me cosine of 0. And if I apply the limit here, we're going to get 5 of 0. That's going to be 1 minus 1 over 0, which is 0 over 0. And darn it, I got to go back and erase those equal signs because we ended up with the old indeterminate form, but that's the L'Hopital indeterminate form. So therefore, by L'Hopital, we can say that the limit of our original function is going to be equal to the limit of the derivative of the top and the derivative of the bottom. So the derivative of the top, if I take the derivative of the top, the 1's going to go away. And the derivative of cosine is negative sine, but it already has a negative in front of it. So that's like a double negative, and it just becomes positive as a result of that. And the derivative of the bottom is 5. And then we're going to go ahead and try our direct substitution here. And that's going to give me sine of 0. And I can go ahead and put an equal sign here because since there's a 5 in the bottom, we're not going to have an indeterminate form, so we're good to put equal. And then we have 0 over 5, which is just 0 is the answer. All right. Let's go ahead and check out maybe 1 or 2 examples here. All right. We're going to do some direct substitution there, and here, and here. So we've got 0 on the bottom, so we know that's probably going to end up being an indeterminate form. The 1 stays there. And by plugging in 0 in those parentheses there, we just end up with pi over 2. Sine of pi over 2 is 1. So once again, we end up with 0 over 0, just like we would expect. And therefore, by L'Hopital, we have the limit as x approaches 0 of 1 minus sine pi over 2 plus x over x equal to the limit as x approaches 0 of, all right, the derivative of 1 is 0, so that's just going to go away. The negative 1 is going to stay in front of the sign there. The derivative of sine is cosine. And this is actually a chain rule situation because there's an inside. So what's the derivative of this inside here? Well, that's just going to be 1. So there's no point in putting a number in the front. We can just leave it as a negative cosine. The negative came from here, right? Derivative of sine was cosine, and then my inside's derivative was just 1, so it didn't really do anything. And then we do the derivative of the bottom, which is 1. And then we go ahead and do direct sub again. And this time we don't got to worry about not putting equal signs because we have a 1 on the bottom. So if you plug in 0, you're going to be left with cosine of pi over 2, which is 0. And so once again, we end up with just 0 as a final answer. All right, let's go ahead and got one more example before we call it practice. So direct sub here, here, and here is going to give me that. And that's just going to be 0 on the top. Cosine of 0 is 1, so we end up with 1 minus 1 on the bottom, which is 0 again. No surprises there. So by L'Hopital's rule, we're going to say that the limit of the original function as x approaches 0 limit of this new function as x approaches 0, and that new function is the derivative of the original one. So the derivative of the top is going to be 8x, and the derivative of the bottom, once again, the 1 is just going to become 0. The derivative of cosine is negative sine, but it already has a negative in front of it. Double negatives cancel, so we're going to be left with a positive sign. And once again, we have a chain rule here, so the derivative of the inside is 4, so I'm going to put a 4 there. And then this is, we're ready for another direct sub. But if I do a direct sub, we're going to get 8 times 0 is 0. And since sine of 0 is 0, we end up with another indeterminate form. So this is one of those situations where we're going to have to do L'Hopital twice. Okay, because we got another indeterminate form. So we say, therefore, by L'Hopital, we can say that the limit of this guy is equal to the limit of the derivative of the top and bottom. So that's going to be 8 over 4 cosine of 4x. And once again, we're going to multiply the bottom by, so the derivative of sine is cosine, so that's where that came from. Then we need to do another derivative of 4x, which is another 4 on the outside. And that's going to cause this 4 here to become a 16 instead, actually. And then we do our direct substitution. We're going to get 8 over 16 times cosine of 0. If you plug 0 in there, cosine of 0 is 1, so that's just going to be 1. And so now we have 8 over 16, which is 1/2. Final answer. All right. So that was an example where, once again, we had to end up doing L'Hopital twice. Sometimes that'll happen. All right, well, let's go ahead and get you guys some student practices to do. All right, guys, so here's 4 problems for you guys to try out. Go ahead and pause the video here, and when you unpause it, we will have the worked out solutions for these. Okay, so I didn't show the part where the direct substitution results in an indeterminate form. I also didn't write the part that says therefore by L'Hopital, just because I'm running out of space. But I wrote the part that I figured you guys would probably want to see, which is the derivative followed by the final answer. So the original problem here was this, which does result in an indeterminate form if you do direct substitution. So we take the derivative of the top and the bottom, and it gives us this new limit. And when you plug 0 into secant, you just get 1, whether you square it or not. And so you just basically have 2 times 1 over 3, which is 2/3. Number 6 over here, once again, same thing. You get indeterminate, so we can use L'Hopital. And we take the derivative of cosine, and we get negative sine. We take the derivative of negative cosine times 4x, or cosine of 4x, which results into a positive, because when you take the derivative of cosine, you get negative sine. There's already a negative here, so it's plus. And then you get a 4 in the front because of the derivative of the inside. It's a chain rule. And so you have 4 sine 4x, and on the bottom it's just 1. Direct substitution makes the top just become 0, and so 0 over any number is always equal to 0, so that's your final answer on that. For this one, number 7, we actually had to do the L'Hopital's rule twice. The first time you do L'Hopital's rule, and you take the derivative on the top and the bottom, you should have gotten 2 sine of 2x over negative sine of x. But that still results in an indeterminate form when you do direct substitution. So we take the derivative again. So the derivative of this one would give us 4 cosine of, this actually should say 2x. There we go. 4 cosine of 2x over negative cosine x. Direct substitution, basically cosine of 0 is 1. So you basically end up with 4 times 1 over negative 1, which is negative 4. Last one here. Applying L'Hopital to this, the derivative would give us 2 cosine of 2x over 5 cosine of 5x, chain rule. And then when you do direct sub, the cosine of 0 becomes 1. So you basically have 2 times 1 over 5 times 1, which is 2/5. Right? And so that's finding limits of trig function. Okay, so let's talk about the limits of trig functions at infinity. In other words, what happens as x goes off into infinity? Well, I've got them grouped here because these ones that are grouped together behave in a similar fashion because their graphs look the same. Both sine x and cosine x have a similar looking graph. They just basically look like a wave. So if I were to ask you, if I were to put this on an x and y axis like this and narrow there, well, as x goes along off into infinity, what y value are we approaching? Well, the y value is not really approaching anything because it's just bouncing back and forth between different values. Like usually it's just +1 and -1 if there's no transformations on it. So the y value just bounces back and forth between 1 and -1 forever. It never really gets closer and closer to anything. And we call that an oscillation. There's the word down there, oscillates. We call that an oscillation. Oscillation means things that rotate or have a periodic or repetitive type of behavior back and forth. So trigonometric functions oscillate. And so if you're trying to find the limit at infinity for sine or cosine, it doesn't have one. The limit doesn't exist because it's not approaching anything in particular. It just continually bounces back and forth between two fixed values. Okay. Now tangent and cotangent, they look a little bit different. Tangent and cotangent both have a pretty similar shape. They're just, one is kind of like the reflection of the other, but that doesn't really affect what we're trying to do here when we're trying to find the limit at infinity. Tangent and cotangent look like this. With these little vertical asymptotes in between them. And once again, as x goes off into infinity, as we move off into the right or the left forever, there's no y value you're approaching because the graph, it starts low and then it goes up and then it reaches an asymptote, then it starts low and it goes up, starts low, goes up, starts low, goes up. It really never really meets anything. And unlike the sine and cosine graph over here, which bounces back and forth between two fixed numbers like 1 and -1, these guys actually shoot off into infinity. So it's funny, as x proceeds to the right, the y value shoots up into infinity, and then all of a sudden it pops up out of negative infinity and continues the process. So It just oscillates between positive infinity and negative infinity. And once again, that just means that the limit doesn't exist. And secant and cosecant actually do the same thing as tangent, but their graphs do look quite different. Secant and cosecant kind of look like these weird little U-shapes here. And they also have these vertical asymptotes. So as you move to the right forever, right, x starts really high over here, and then it goes down a little bit, but then it shoots up. And once it passes this asymptote, it starts down here at negative infinity, and then starts to shoot back up until it reaches there and climbs back down until it reaches to negative infinity. And once it goes there, it starts back up here at positive infinity and crawls down. So it's just bouncing back and forth once again between positive infinity and negative infinity. It never really reaches any specific y value. Okay? Unlike a regular limit, right? Like if you had a horizontal asymptote, as you move off to the right, the y value is reaching a specific flat y value. But all of these guys here, trig functions oscillate. They just go up and down constantly. And so they never really approach any particular limit. And so because of that, let's go ahead and come up with some quick little rules once again. And I put these on the flashcards that I printed out for you guys in your notes handout at the beginning of the year. So you should have these on some note cards. Good little things to be aware of. Anytime you're taking the limit of a trigonometric function as x goes to either positive infinity or negative infinity, the answer is it just doesn't exist because it oscillates. Okay? So that's the basic thing I want you guys to be aware of. Now, there is a slight difference, though, between sine and cosine and the other four, which we talked about. Sine and cosine bounce back and forth between fixed numbers, whereas the other ones bounce back and forth between infinities. And that'll result in some outcomes when we get down here. So let's read on. Now, if you have an infinity up here, and you're dividing it by some trig function at infinity, well, on the bottom then, that means that you're oscillating. The value's oscillating. Well, it doesn't really matter what's happening here. Since this number on the top is getting bigger and bigger and bigger forever, it doesn't matter what's happening here on the bottom because it's just basically shooting off into undefined anyway. It doesn't exist, but it is oscillating nonetheless because every time this thing bounces up and down, that pulls the infinity with it. So the infinity will slightly change as this alters, but there it is. So basically, if you have a trig function on the bottom and something on the top that's going off into infinity, your answer is just going to be the limit does not exist and it oscillates. Okay. What if you have an oscillation on the top? Well, let's talk about sine and cosine first. Now, sine and cosine, as I said, they really only bounce back and forth between 1 and negative 1, unless you're multiplying them by something. But for the most part, they pretty much just bounce back and forth between two numbers. Well, if you're dividing that by infinity, you guys remember the rule we had in one of our last lessons, which is where if you have a number on the top, you divide that by infinity, that equals 0, right? Well, that's the same thing here, because the number on the top never really gets very big. It just bounces back and forth between 1 and negative 1. And so as this bottom here just explodes off into infinity, it basically is just like having a number over infinity and 0. But that only applies to sine and cosine. And the reason that only applies to sine and cosine is because, as we mentioned with these guys here, these do not bounce back and forth between 1 and negative 1. Instead, these ones bounce back and forth between infinities. And so when you're dividing an infinity by an infinity, who knows what's going to happen. But we do know that it's oscillating here, so it's never really reaching anything in particular if you have a tangent, cotangent, secant, or cosecant. It's oscillating, it's bouncing back and forth between infinities. But regardless of what the bottom's doing here, even though the bottom's getting bigger forever, the top doesn't really allow us to have an answer. This one just does not exist. So we have these four situations. The limits of trig functions at infinity never exist. If you have an oscillation in the denominator, we're just going to say that the answer doesn't exist and the problem oscillates. If you have an oscillation in the numerator with infinity in the bottom, and that oscillation is due to sine and cosine, we're going to say 0. if you have an oscillation in the numerator, and that's due to tangent, cotangent, or cosecant, or secant, then we're just going to say does not exist. Just so you guys know, the software that I give doesn't really do this, but I'm just kind of mentioning it. You will see this a lot. You will see this a lot, and you will see the top one a lot. This fourth one, I just wanted to talk about it, but you probably won't see it a whole lot. Okay.
And then I forgot to add this one here. If you ever have an oscillation being multiplied by infinity, that's a D and E that oscillates. And the reason for that is, as you guys know, an oscillation is something that wiggles like this, right? But if you're multiplying it by infinity, what happens is at first it starts small, but as you multiply bigger and bigger numbers, and as it gets farther and farther into infinity, it just increases. And so it's still an oscillation, and the Y value doesn't really approach anything in particular. And so we would say that that too is does not exist due to oscillation.
So, all that being said, let's go ahead and put that concept to work for us. Let's look at some sample problems. Okay, so let's do some direct substitution here. If I did some direct substitution, put infinity in there, that's going to be negative infinity. And 1 over infinity. Now we know that 1 over infinity is 0, right? So what we really have here is cosine of 0. You have a number over infinity, it just always equals 0. And cosine of 0 is 1. And 1 times negative infinity is just negative infinity. So there's our final answer there. That one comes out to be infinity. Okay? Go ahead and take a look at number 10 here. We have, let's do our direct substitution. I'm going to use arrows because we're not sure if these are going to be defined answers, like we actually get a limit. It may be undefined, so we just want to make sure that we arrows instead of limits or equal signs for now. So I'm going to plug this in. We have a negative in front of the entire fraction, first of all. And if I replace x with a negative infinity, get that. Down here on the bottom, we're going to have cosine of 1 over infinity. And we talked about this before, right? The 1 over infinity is 0, and cosine of 0 is 1. So what we end up with is we end up with a negative infinity over 1. And the double negatives here just cancel out to become positive infinity over 1, which is infinity. So that one's also infinity. As for this one here, if we do our direct substitution, we're going to get cosine of negative infinity. And we talked about this on the last slide. Anytime you're finding the limit of just a basic cosine function at infinity, it's undefined, it oscillates. So we're not gonna say infinity, we're gonna say it does not exist, and we're gonna say it oscillates. It doesn't go to infinity. Why not? It doesn't go to infinity because it goes up and down, right? What this means by putting a negative infinity in here is that means we're moving to the left forever. And as I move to the left forever, what's happening? Well, my graph's just going up and down constantly between two fixed values. The y value never really is approaching anything in particular. It goes back and forth. It's oscillating. And so that would be our answer for that one. Go ahead and take a look at this one here. So if I apply the limit to the sign, we're going to get sine of infinity. And on the bottom, we're going to get infinity. And then if you take the limit of a constant, the constant just stays the same. So I'm just going to put that there. Now, sine of infinity is like the one before it. It's an oscillation. I'm just going to abbreviate that OSC. Now, on our last slide, we saw that when you have an oscillation over infinity, that's just like having a number over infinity. And so that's just going to be 0. Okay, so we end up with 0 plus 1. That one actually has an actual limit associated with it. The limit actually equals 1. Okay. So there you have it. So let's see if you guys can practice some of these. All right, so go ahead and pause the video here and try these 3 problems and see what you guys get. When you unpause it, you will see the solution. Okay, so here's our answers. For number 1, if you plug in infinity, you get 2 times infinity times cosine of 1 over infinity. And we've done this a few times now. Cosine of 1 over infinity is just going to be 1. And if you do 2 times infinity times 1, you just get infinity. On the bottom here, this is the number 15. That's kind of an interesting one. We have 2 times infinity times cosine of infinity. Now, cosine of infinity is an oscillation. But remember, that just means it's bouncing back and forth between two fixed values. So it's just like a number, basically. Now, if this was tangent or something, that would be an infinity, and it would be switching back and forth between positive infinity and negative infinity. We would just say it doesn't exist. But in this case, since the oscillation is between two fixed values, two numbers, basically, no matter what you pick, you're always just multiplying infinity by some number, and therefore, you're going to end up with just infinity. So it's the basic point here is that whenever you're doing cosine or sine at infinity, it's oscillating, going back and forth, but it basically behaves just like a number almost. But if you're dealing with tangent, secant, or cosecant, it oscillates, but it doesn't behave like a number. It acts more like an infinity because it oscillates between infinities. All right, let's go ahead and take a look at number 14. Plugging in the negative infinity here, we end up with this expression. Now, cosine of negative infinity is oscillation. But that's the cosine, so this oscillation is just like a number. So it's like you have a number over infinity, which is just 0. And so we end up with 0 plus 4, which is 4 as a final answer. All right, let's go ahead and see what else we got. So these are some trickier examples here. Now, let's go ahead and see what would happen. So first of all, if I did direct substitution, I'm going to get sine of 0 times sine of 0. Now, both of those are 0, so you basically just end up with 0 on the top. And then you're going to plug in 0 for x here and 0 for x here. So that's 0 times 0, which is 0 here. And as you can see, that's not an answer, but that's a sign that we're probably going to do L'Hopital's rule, right? But now we could do L'Hopital's rule on this, just the way it is. But I'll tell you that even though that might be the more direct and simple way of approaching it in your mind, because it's like, well, that's the obvious step, the problem is procedurally, that's actually going to be pretty hard. Because as you guys can see here, this is a product rule. Because, and in that product rule, you've got a chain rule. So finding the derivatives of both the top and the bottom here is going to be a little bit hard. But we're gonna instead of doing the product rule, what I want to do is I want to reintroduce you guys to a really cool application of a limit rule that we learned earlier. You don't need to write this, but I just want you guys to watch for a second. A little while ago, we talked about properties of limits. Okay, so if you have the limit of f of x times g of x, you can find the limit of this by taking the limit of f of x at a and the limit of f g of x at a separately, and then just multiply them together. And that's kind of how we're going to handle this here, is we're going to split this expression up into two separate things, and we're going to take the limit of each one separately. And trust me, it's a lot easier than trying to apply the product rule to this. Now, if you did do the product rule, it will work. It will just be very tedious and a lot of steps, and that leaves a lot of room for error the more steps that we take. And so this strategy I'm going to share with you is definitely preferable to just doing the product rule. So first of all, to take note of the fact that yes, by L'Hopital's rule, or by the indeterminate form, we know we have to do L'Hopital's rule. But first, before I even embark on starting L'Hopital's rule, I'm going to start by rewriting this. I'm going to take one of my factors on the top, and I'm going to put it over one of my factors on the bottom. And then I'm going to put a times symbol, and then I'm going to take the other factor on the top and put it over the other factor on the bottom. So all I've done is I've split my fraction up into two separate fractions that are being multiplied together, and that's just an algebraic move. But the reason I wanted to do that is because now I could take the limit of these two things separately then. I could take the limit of this one first, and then I could take the limit of this one over here second. And it will be much easier than doing the product rule from the beginning. Trust me, I've tried it. Okay, Now, just so you guys know, both of these limits result in an indeterminate form, okay? So we're going to have to do L'Hopital on both of these. So, and you guys can check the work. If you plug 0 in, you get 0 on the top and 0 on the bottom. So we have to do L'Hopital on that particular limit. Same thing over here, 0 and 0. So we need to do L'Hopital on each of these pairs separately. So if I do L'Hopital with the first one here on the left, we're going to end up with, and I'm showing my work a little bit differently this time just because of space and time, but I'm not going to rewrite the original problem and say it equals this new limit. I'm just going to rewrite the limit now with the derivatives just to save space and time. So the derivative of the top here is going to be 2 cosine of 2x. We get a little bit of a chain rule going on there. And the derivative of the bottom is 1. And then we're going to do the derivatives of this one as well. So the derivative of sine is cosine. And the derivative of sine of 4x is going to be 4 cosine 4x. And now we do our direct substitution. Cosine of 0 is 1, so I basically have 2 times 1 over 1, which is just going to be 2. And then cosine of 0 is 1, and cosine of 0 is 1, so I have 1 over 1 over 4. So now I've got 2 times 1/4, which can be simplified to 2/4, which can be simplified to 1/2 is the final answer for that. So, step 1, split the products up into 2 separate fractions. Take the limit of each fraction separately, and in this case, both of them required L'Hopital's rule, which gave me this. Then the direct substitution just yielded an answer nice and neat. Now that seems a little bit more complicated, and it is, than the others, but trust me, it's a lot easier than trying to do the product rule. The product rule would have been quite messy. All right, let's go ahead and do another one. Now this one, believe it or not, is actually the same kind of problem. It just doesn't look like it. But it really is. Let's go ahead and give it a shot here. So we're going to need some space. First of all, if you do your direct substitution, as you can see anyway, you get 0 over 0. That doesn't really matter. I'm going to actually start by rewriting it. How are we going to rewrite this? Well, sine squared of 4x, you guys know what that means. You know that means we have sine of 4x being multiplied by sine of 4x, doesn't it? And on the bottom, 4x squared, doesn't that mean we have 4x times x? So I just split up the terms that have x's in them. That way I can actually make 2 separate fractions out of these with a x in the top and the bottom. Now some of you guys might have thought, well, instead of splitting up the 4x squared into 4x and x, couldn't we have just done 4 on one of them and x squared on the other? And the answer is unfortunately no. You guys know that when you're doing L'Hopital's rule, you have to have a variable in the top and in the bottom. If you don't, you're not going to get that indeterminate form, so you can't apply L'Hopital's rule. Okay, so I did have to split the 4x squared up so that you end up with an x in each of the fractions of the denominator. All right, so there it is. So I split up the sine squared into 2 sines, and I split up the 4x squared into a term with 2 x's in it. So that way I can have 2 separate fractions with x's in the top and bottom. All right, now we're going to distribute that limit into both of them. So I'm going to take the limit of my first fraction there. And then I'm going to take the limit of the second fraction there. Direct substitution, once again, is going to give me L'Hopital's indeterminate form of 0 over 0. So we're just going to go ahead and take the derivative of the top and bottom now. So the derivative of sine of 4x is going to be 4 cosine of 4x. And the derivative of 4x is 4. Over here, for the limit on the right side, the derivative of sine of 4x is once again 4 cosine of 4x. And the derivative of x is 1. So I'm running out of space here, so I'm going to erase some of this stuff above. Okay. Now, direct substitution here, this cosine of 0 is going to be 1. So you have 4 times 1 over 4, which is 1. And here, cosine of 0 is 1, so 4 times 1 over 4 is 4. And so 1 times 4 is 4 will be our final answer. That would be the limit of this particular little trig function. So how can you know when you need to do that? Well, it takes a little bit of recognition. But I mean, basically, the idea is, can you split this limit up into two separate fractions that are being multiplied together? If so, well, then just know that is an option. Just know that that is an option. It may or may not be the best one, so if you try it doesn't work, maybe try it the old school way from the first few examples. But basically, if you can split it up into two separate fractions, that's kind of the way to. So here's one for you guys. Go ahead and see if you guys can find this limit. Pause the video. When you unpause it, you'll see the solution. All right, so here you go. This is how I would have split the fraction up into two separate fractions being multiplied. Next, we distribute the limit to each one of them. L'Hopital's rule applies because both of them result in an indeterminate form. So the derivative of the one on the left here is what you see here on the left. And the derivative of the one on the right is what you see here on the right. And then doing direct substitution for the one on the left results in 5. Doing direct substitution for the one on the right results in a third. And 5 times a third is 5/3. The final answer. Okay. And so that's doing limits with trigonometric functions, primarily using L'Hopital's rule. So see you next time, guys.